So let's say there is a table with n positions. Okay, so let's say 1, 2, 3, 4. Let's say four positions. Okay, more. Let's say more. Let's say just 4 positions. 1, 2, 3, 4. Okay. So there is a boy called Magnus. So in our game, he's called Magnus, who wants to visit all the positions in the table. Okay, so at the beginning he is at position 1. Okay, and then at each time he can declare how many positions he wants to move. Maybe if he moves for 1 position, he will go to 2 or 4. If he moves for 2 positions, he will go to 3. Is that okay? 3 positions doesn't matter, so this is imaginary. For 3 positions, he will go to either 4 or 2. Is that okay? So Magnus at each time, he will declare how many steps he wants to move. And then there is another one called Derek. Okay. So Derek. So this Derek. There's another one called Derek. Derek is another person. So once Derek doesn't want Magnus to move to all the positions. He wants to avoid Magnus to move to all positions. So what Derek can do is that Magnus just tells how many steps he wants to move, but Derek decides the directions, whether Magnus should move clockwise or anti-clockwise. Is that okay? Okay? So Magnus starts at a location, and then Magnus first declares, okay, I want to move how many steps? And then Derek says, okay, then you move clockwise or anti-clockwise. After that, Magnus moves to a new position, and then Magnus declares another number of steps again. And then Derek decides the direction. So Magnus decides the magnitude, and then Derek decides the direction. Is that okay? Okay, now, here, for 4 positions, then we will see that Magnus, no matter how Derek do, no matter how Derek does, Magnus can always go to all the positions. Magnus do this, so he starts at position 1, right? Then Magnus says, okay, I want to move 2 positions. No matter what Derek does, Magnus will go to 3, right? Either clockwise or anti-clockwise, he will go to 3. Is that okay? Okay? And then after that, Magnus says, okay, I want to move 1 position. Okay, no matter what Derek does, Magnus will either go to 2 or 4. Magnus will still be happy, because after that, Magnus will say, I want to move 2 positions. Then Derek cannot deny Magnus going to all 4 positions. Is that okay? Everyone is clear about this question, right? Right? Okay, so this question, we want to show that if the number of positions is a 2 power, then Derek cannot avoid Magnus visiting all the positions. Okay? Okay. How we can show? Yes. The first idea that comes to our mind is like induction, right? Yeah, try induction. Okay? So this is question number 5. And then finally, the last question number 6. Question number 6 is a just for fun question. Okay. So this is about a game. Okay, so let's say there is a borderline here. Behind the borderline, there are a lot of chess pieces. They are, let's say, arranged nicely on a chessboard. Okay, so that so on a regular chessboard, let's say. So let's say not that regular, okay, square chessboard, okay. So that each position there is a piece at the beginning. Is that okay? Now, we can do certain kind of movement of the chess piece. So the moving rule is very simple. If there are two adjacent pieces, so like this one or like this one, and there is an empty space immediately next to them, let's say there is an empty space here or there's an empty space here, then for this one, you can jump this piece over and then onto this piece, so that these two position becomes empty, and this piece will be there. Let's say this is this one. You jump over, and then this will become this one. Is that okay? And then for this case, let's say this is the piece, and then what we can do is that we jump this one over this one, so that it becomes this one, and then the two pieces are gone. Is that okay? Is the roof clear? Okay, so it has to be adjacent, touching, and then this one is also touching, so you can jump. Okay? Now, here in this question, we want to try to send the piece as far away from this line as possible into this direction, as far away as possible. So first of all, is it possible that we can send a piece to one position above this line? Then this will be very simple. I just jump this piece over to this one, then we can send it to one position. Am I correct? Is that okay? So I can do something and send a piece. Let's say this one jumps to this one, then again, I can send this piece here. Is that okay? Now how about two positions? Is it possible to go to two positions? Now two positions, yeah. Maybe. So after jumping these two, then these two are gone, right? So I can further, let's say this is this one. So I can jump this piece here, and then jump this piece here. Is that okay? So it is possible to have a piece sent to two positions above this line. And then, okay, this would be one. How about three? How about three positions? Let's try. Assuming that we have enough pieces at the beginning, okay? Three, is it possible? So let's say I jump this one to here. Is that okay? So let's say I jump this one to here. So I will have this one. Okay? And then I jump this one to here. Is that okay? So this time, I jump this one to here. So I will have this one becoming here. Is that okay? Then nice. Then what we can do, I jump this to this position, and then I jump this position, and then we can send something to here. So these are now gone. Okay, so far, if you understand the rule, could you please raise your hand? Okay, now the question here is that we want to show that the maximum possible is equal to 4. Okay, we are not going to show that it is equal to 4, because in that case, you need to find a way that you jump to 4. But here, we want to show that you cannot do more than 5. Is that okay? So, understand the question? Okay. Okay. So this question turns out to be, we need to use a different proof techniques to help. So let me show you the related proof technique. So far, everybody understand this one, right? Okay. So if it is like 5, so this is 5 positions. It is not possible if the board is finite. If it is infinite, then maybe it is possible. Infinite, this is the limiting case, 5. So in any case, you cannot go to 6 positions. 6 is impossible. Okay? So what is the related concept? So I will tell you a related concept. So the idea is to make use of something called invariant. We're going to use an idea called invariant. So invariant is something that doesn't change. It means it does not change, not varying. And then in some of the proofs, if we can figure out something that is not changing, okay, this not always not changing, then then we can make use of this fact to help us to simplify the proof. So not changing could be something like in terms of sorting. Okay, if we are doing what? If we are doing the selection sort. Selection sort. So we look at the cars, we pick out the smallest one, and then we pick out the second smallest one, and then we pick out the third smallest one. So there is something invariant. The invariant is that what we have finished working is a sorted sequence. Okay. So this is like an induction idea, right? So what we have done remains unchanged. What we have done remains sorted. Okay. Now, our related problem of this one is that, okay, so let's imagine we have a game and a chessboard, okay, infinite size. So infinite size. And then at the beginning there is just one piece here, so infinite size. Let me write down. So it's like this. Okay, infinite in size. At the beginning we have a piece here. We have a piece here. And then we can do movement. The movement here is not like that. It is like we can replace a piece with another piece on the top and another piece on the right. Is that okay? And then for this piece, so we can further do, so we can select any piece that we like and then replace it by one that is on top and one that is on the right. Is that okay? Is that okay? Now, for this one, then we cannot do so. The reason is that each square can hold at most one piece. Okay. So, but still we can move this out. So we can move this, replace it by a piece here and a piece here. Is that okay? Now the question here is that, so the board is very, very large, infinite. Just like that, infinite. You have infinite pieces and an infinite size. And then let me call this red a boundary. There is a boundary here. Okay, we want to ask, if you continue the movement, is it possible that you can make this 10 squares empty? Now, first of all, can we make this 1, 2, 3, 4, 5, 6 square empty? Let's see, I don't know. But at least there is a way to make the first 3 pieces empty, 3 squares empty, right? Because after that, I just move this out. And then I have something like this. Is that okay? Then these 3 squares are empty, right? And then maybe I can still move this out. Let's see, let's try. I can move this out and see what will happen. Then I will make more empty space. And then let's say I move this out. I will make this more empty. Is that okay? And then maybe I move this out. And you will see that it's getting more and more difficult. And then I can move this out. Is that okay? And then I can move this out. Is that okay? And then I can move this out. Is that okay? And then, so what I'm trying is I try to make these three empty as well. Let's see if I can do so. Yeah, maybe. So let's say if I can move this out. So let's see. I'm not sure. Let's say I move this out. I have this one, and then move this out. I have this one. Move this out. I have this one and this one. But this one is gone. And then move this out. Look at this. Is that okay? Wow. And then I try to move this out. And hopefully this one can be moved out. Hopefully. This one can then be moved out, so that this one can then be moved out, and then this one can be moved out. Hopefully. Okay. I don't know how much time that I need, maybe a lot more than I think of. But here, so you see that, so at the beginning, to make these 3 squares empty, it is easy, right? And then perhaps, to make these 6 squares empty, it is still easy. But on the other hand, we want to show that, amazingly actually, that it is impossible to make the 10 squares empty. Now how we can show? How we can show? This one is a nice problem that we want to figure out something that is not changing. Let's do this again. Well, originally there's one piece, right? But suddenly, after one step, this piece will now change into two pieces. So the number of pieces is not unchanging. Okay, you will say that the invariant is that the number of pieces is increased by one after each step. So this is correct, okay. But this does not help us, okay. So something that is more basic or more related to the work here is that somehow I want to relate this piece to these two pieces. Okay. So that somehow after one step, okay, there is something not changed. And further, if I have this piece changed to these two pieces, I want to relate this piece with these two pieces. So that after one step, nothing is changed somehow. Okay. Now, this is my idea. So this is the board at the beginning. Okay. Let's make the board label. Okay. So this square, I give it a label 1. Is that okay? Now these two square, I give it a label 1/2. Is that okay? And these 3 square, each of them, I give it a label 1/4. And then 1/8. And so on. So and so on. So this is going to be 1/16, 1/16, 1/16, 1/16. This one also 1/16. Is that okay? And so on. So what is not changing in that case? So at the beginning, the board will be like what? At the beginning, the board will be like, you just have a piece here. Am I correct? After one step, then the board will now be changed to, I have a piece here and a piece here. Is that okay? What is not changing? With the help of the labeled, what is not changing? So the next step, let's say I change this to this one. I move this piece. So next step, let's say I'm going to move this to like this. So what is not changing? The sum, yes, the sum. The sum of all the pieces, that's all you have. The sum of all the squares with the piece. Is that okay? It's not changing. It is always equal to 1. Am I correct? It's always equal to 1. Okay. Then what is the boundary that we are looking at? So this is the boundary that we are looking at. So this is the boundary that we are looking at. If we say that if we want all these places are empty, then what does that mean? It means that all the chess pieces are on this side, right? And then it can only happen, okay? It can only happen if there's 1 here. Let's figure out how much value we have on this side, okay? So how do you get this? So let's calculate the total value of this side by counting all the values and then deducting the values inside this part. Is that okay? So this is something nice. So let's calculate the value of the whole world, the whole board, by counting column by column. Okay. So for this column, it is like 1 plus half plus 1/4 plus 1/8, and so on and so forth. So for this column, how much do we have? 2. Okay. And then for the next column, we get half of it, right? So we get 1. And then the next column, we get 1/2. And then the next column, we get 1/4. And then the next column, we get 1/8. Is that okay? So in the whole world, it is like, if you sum them up, it is equal to 4. This is the whole world. And then how about these 10 squares? So it is like 1, and then 2, and then 3. 3.25. Is that okay? So all these 10 squares adds up to 3.25. So what does that mean? The outside has only 0.75, right? It's less than 1, strictly less than 1. That means that even if I give you infinite space, and then all of them are holding pieces, then it is impossible to make this empty. Is that okay? Okay? So actually, it is going to be very hard already to make these 6 squares empty. So if you add these 6 squares, it is like 2.75, right? 2.75. 2.75. So I need to have, so remaining part is just 1.25, and then I need to hold 1. So actually I need already many pieces in order to have this hold. Okay? But here, if we can obtain this invariant, suddenly the problem becomes very simple. It's just like summation of this geometric progression. Okay. Now this one is also like that. We have some hints for you for this question. Okay. Okay. So it's been a long while for me to talk about things. Let's take a 10 minutes break and then we come back for the lecture. Okay.